much for the invitation. It's a short talk, so it's going to go fast. But I'll try to tell you what has been happening in the 3.5 keV front, line front in X-rays. So we have been talking about annihilating dark matter up to now, but there is another well-motivated dark matter particles, decaying dark matter particles. The most famous ones are sterile neutrinos. These particles decay into a regular neutrino by emitting X-rays. And these X-ray photons can be detectable through the X-ray data we have in the archives. And let's say if you detected a line, the flux under this line is basically proportional to the decay rate or mixing angle, and the energy of the detected line is half of the energy, the mass of the particle, okay? So because this is a monochromatic decay. So our motivation in 2012 when I came along was basically to search for the parameter space of these particles. So this is the mass and mixing angle parameter space. And by the time I actually started working on these particles, searching for these particles, most of the parameter space was excluded by previous X-ray searches. But there was a lot of white space needed to be explored. This plot actually looks a lot different now, but this was our motivation in 2012. Okay, so the next step is basically to look for best targets you might want to search for. For this, we actually went after galaxy clusters, because they are the largest collapse concentrations of dark matter in our universe. So if you look at one of these objects, they would look like this. And what you see here is member galaxies. These are bright spots. And in between these galaxies, it's filled with hot intracluster gas. And this gas is too hot, 100 million degrees hot. But most of the baryons, actually, you see in this picture, makes up their 15% of their mass. 85% is in dark matter. That's why they are really good targets for dark matter searches. So we decided to go after these targets. But beyond that, I think the most important reason is that they have really relatively simple physics compared to galaxies, for example. They emit this hot intracluster gas, emits mainly through thermal Bremsstrahlung, and that gives you a continuum emission. On top of that, you get emission lines, for example, like this. The most prominent line is iron K line at 6.7 keV. These emission lines come from K and L shell transitions from this kind of plasma. So thermal Bremsstrahlung is the continuum under this spectrum. You can almost draw with your eye, okay? It's a very well-calculated theoretical spectrum. And the K-shell and L-shell transitions are well studied in the lab, so we know what to expect from this kind of plasma. We have been observing these objects since 1970s when we launched first X-ray telescope. So there is no surprises, and it made sense to go after these guys. What we are looking for is basically an emission line like this one, but much fainter than that one, which could be produced by decaying dark matter particles. All right, so this is the 2014 paper. To actually probe that white space, blank white space, you need to increase the sensitivity in your observations. How do you do that? You increase the exposure time, right? It's straightforward. To do that, you either send a new telescope in the sky, which is that's not what we did, or you stack all the observations exist in the archive from galaxy clusters. And that's exactly what we have done. We stacked 200 observations from galaxy clusters in the XMM Newton archive. The reason why we selected XMM Newton, because it has the largest collective area and effective area compared to other X-ray satellites in the sky. And we stacked them on their rest frame. When you stack actually these clusters on their rest frame, the source signals actually align very nicely, and anything other than source signal, I'm talking about, for example, X-ray background, instrumental background, they smear out, okay? Because they are frozen in the detector frame. So in these kind of dark matter searches, instrumental background is a challenge. Any instrumental line can actually mimic your dark matter, faint dark matter line, so you need to get rid of that. But we have done this from the beginning. So by this way, we made our analysis very sensitive to dark matter lines. Here is what we found. We modeled actually wide X-ray band, but we found in 3 to 4 keV band this little bump. And that was the only bump we found in our spectrum, in fact. And I'm zooming here to be able to actually, for you to be able to see this little bump. It is 1% bump over the continuum. It's really faint. So you have to be very careful how you model your spectrum, because you may just miss it. When we modeled this little bump, we saw that it's actually significant. We also take into account the look elsewhere effect. After doing that, we saw that it was 4.5 sigma significance. So the other test we have done in our 2014 paper was to actually compare different type of galaxy clusters in our sample. We divided our sample into several subsamples. We looked at distant clusters, we looked at nearby clusters, and we looked at the X-ray brightest cluster, Perseus cluster. And we saw that Perseus cluster was actually much more brighter compared to the other clusters in our sample. So make a note of this. Remember this. I'll come to this one. But remember, Perseus was anomalously bright. Where are we now? Well, there has been a lot of debate on this. There are a lot of independent detections, significant detections, but there are also non-detections in the literature. So most of the non-detections are basically consistent with the 3.5 keV line, which was detected in stacked clusters. But one of them came from stacked galaxies. They placed pretty strict upper limits on the flux of the line. This was particularly 5 sigma, I think. But today, I'll talk about 2 new studies came out this year, 1 non-detection, 1 detection papers. So let's talk about the good news detection paper. Capellucci et al. Has looked at Chandra observations of the blank sky fields. So he's particularly stacking here Hubble Deep Field North Cosmos and Chandra Deep Field South observations with Chandra. These were 10 megasecond observations, okay? So his idea was actually to study X-ray background, and then he realized that there was a little bump around 3.5 keV. So he realized that that was a 3 sigma detection, and then he immediately compares the signal with the projected NFW profile from our galactic center. He says he sees that that's 1 sigma consistent with the profile. And then there were actually 2 other detections from New Star. These 2 guys were detected from the same fields from New Star, the New Star Hubble Deep Field North and Chandra Deep Field South observations. They are 12 sigma detections here, and he sees that his detection is 2 sigma away from them. But let's talk about the non-detection a little bit. So we launched this great satellite called Hitomi last year. This Hitomi satellite actually carried a high-resolution colorimeter. This high-resolution colorimeter was 20 times had more resolution than any of the X-ray satellites we have in sky at the moment. After a month, the satellite died. But in that time, we were able to observe Perseus clusters for a very short time. That time was 7% of the time required to observe actually detect the 3.5 keV line. So it was very short. We did not expect to detect the line in these observations. So regardless, it's here, the interesting band, 3 to 4 keV band. And that 3.5 keV line is supposed to be here, okay? There is no line, no shocks. But if you have good eyes, you can see there is a very broad dip at that energy, okay? So how unlucky can you get, right? Not only that there is no line, but there is a dip over there. Regardless, these observations were very useful because we could test our plasma assumptions we made in 2014 paper. So one of the astrophysical explanations of the 3.5 keV line was potassium. We made a note in that in 2014 paper for potassium, because it's really close to our line. To make up that flux excess, it has to be 10 times solar. We resolved that for the first time here. And this potassium line is subsolar. Exactly, it's 0.6 solar abundance here, okay? So it's not 10 times solar. We also could check our plasma temperature and our line ratios. Line ratios are very, very hard measurements to make in CCD type instruments because most of the lines are blended with each other, but they were right on. And they are consistent with the Hitomi observations. So potassium is gone, and there is no very low temperature gas producing a lot of potassium in this plasma. So astrophysical emission in terms of potassium does not explain this line. So let's see what happens in terms of upper limits. Let's imagine that there is a dark matter line hiding in that Hitomi spectrum. And then you fit the spectrum with that, you get this broad dip over here. And if you just calculate the 90% upper limits on that fit, you get this band, red band, and on top of that, we put calibration errors in that lines. Overlaid is the XMM Newton detection of the 3.5 keV line within the Hitomi field of view, and you can see that they are in tension with each other by 3 sigma. And that is the 3 sigma tension that you have been hearing about in the press. But this story is not that simple. Let's look into these observations a little more detail. Here is the, again, spectra, but they are divided into several observations. We had to stack 3 observations to get that overall spectrum. And this dip, which is dominant in the overall spectrum, is actually coming from one of the observations. Okay, and that observation, we realized that it was taken very early on in the life of the satellite, where detectors were very warm, okay, and the calibration was not very well done. And the other observations where the things were stable are taken 1 week apart from that observation here. When the detectors were cool, things were stable. And in fact, if you look back, these humps and bumps are everywhere in the spectrum, and that is the driving observation for the 3 sigma tension. But we didn't want to look biased, and we decided to include that observations in our final stacked spectrum. And if you just exclude that, there is no tension between Hitomi and XMM Newton. In normal conditions, we would not worry about including that observations in our limits, but because the satellite failed, we didn't have any choice. All right, so remember, Perseus was too bright to begin with. If you're wondering where that stack cluster signal would fall in these upper limits, it's shown in that dashed blue line over here. It's so tiny, so faint. Okay, so it's buried within the noise of our measurements, and Hitomi cannot really say anything meaningful about that. Therefore, Hitomi observations are consistent with the 3.5 keV line. Okay, what is next? We desperately need a colorimeter in space to look into the X-ray band. We do need it so badly. When we could have a colorimeter and look at a galaxy cluster long enough, like 1 megasecond, we will be able to tell if this line is an astrophysical line or is a dark matter signal. But before then, it's really hard. We are working our best, though. So the good news is NASA and JAXA just signed an agreement to refly the Hitomi Observatory in 2021. We will have a colorimeter finally flying. And if that fails again, we will have another one in 2028 that's going to be launched by ESA. And in the meantime, there are other alternative tests you can do to test galactic center excess. Okay, that was also a 5 sigma detection, and that's going to be presented by Ranjan Laha tomorrow. So if you're wondering about that test with MicroX, please go to his talk. And here is where we are. Hitomi basically excluded this band on top of this magenta curve, and Perseus is right here. All other detections from M31, this is the deep fields, and then stacked galaxies lies over here. So they seem to be consistent with each other. And I'll stop here and answer your questions.
Great talk. Do we have any questions?
Thank you. You mentioned that the Hitomi data allowed you to exclude the nearby potassium line as a possible source. I thought that the Hitomi satellite looked at one, you got this from one source of spectrum. Is it possible that the potassium abundances are different given that you've stacked all the observations for the original observation? Is there any sort of issue there, or is this very broadly applicable that potassium's out now as an idea?
Good question. Yes, I'm generalizing Perseus clusters to other clusters, basically. The reason is that clusters are very typical objects, so you don't really expect potassium or iron, let's say, to be subsolar in one and then 20 solar in another one. Actually, we have never observed such an abundance difference in between different clusters.
Thank you.
Any other questions we have? I have one more. So you talked about excluding things like the potassium line and known lines, which is something that's easy to do just given better energy resolution.
Yeah.
Is there any possibility that the line is astrophysical but from some chemical origin that we don't know of yet, in which case energy resolution can't be the whole answer to determining the possibility that it's a dark matter line?
That's also a good question. So if there is another astrophysical line there that we have not known, that could be it. Yes, CCD resolution cannot tell anything meaningful about that. Although if you just look at different, for example, sources, and if you see that kind of line, that could be a good answer. But I think the spectral resolution is the key. Because what you want to do is to resolve out everything. And if this is an astrophysical, spectral resolution will resolve it. And that's what we need.
Any other questions? Oh, we have one back there.
Yeah. Could you comment on the status of the hypothesis that this comes from a charge exchange reaction?
Yes, thank you for asking that question, so I get to explain it. So let's see the charge exchange paper. One more. Okay. So let me explain you what this is. So in clusters, we have very hot gas, as I said to you before. But in the centers, you have cold H-alpha filaments. These are neutral gas. What happens is that this sulfur ions, trapped ions, basically steals one of the electrons from hydrogen neutral gas, and that electron can cascade down in the atomic levels, and they can give you very like forest of lines, okay? And they can mimic dark matter lines. And with the CCD resolution, you cannot resolve these lines. With colorimeter resolution, you can. So this idea was first proposed by us in 2014 paper. Then the charge exchange models were not that sophisticated. We studied some of them, but later Liu Gu from Esron actually have worked on this charge exchange model, and now he has much sophisticated models. And that's what he's showing you here. These, for example, this is the XMM Newton PN. I think this is just the Perseus cluster excess. And if you have a charge exchange line, it should appear around 3.44 keV. There are lab experiments right now on this. Okay, it's right here. But this paper really doesn't show you where the most significant signal is, XMM signal is. And it would appear right here, okay? So it's really not near the line at all. But considering CCD resolution, you might detect some of this bump in your line at 3.5 keV specifically. I've tried that. I have added charge exchange models in my spectrum. I added a line around 3.44 keV. It hasn't affected anything. So I think it's not charge exchange, but before we have a better resolution, I will never know for sure.
Okay, you can't, does the fact that you see this like in the Chandra deep fields, is that still consistent with the charge exchange?
Right, so that's another good point. You would not expect to have sulfur charge exchange in the deep fields, right? There's no strict sulfur gas there that hot. So yeah.
Okay, thank you.
Okay, let's thank our speaker again.